Hi everyone, we're back with another installment of Organic Chemistry 1. So I don't usually start my YouTube videos with course goals and themes, but I am going to start this one here just because of this first goal is so central to what I'm going to talk about today, the three-dimensional nature of organic molecules. If organic molecules were not three-dimensional, we wouldn't have this lecture, but they are, and it gives rise to this whole field of chemistry called stereochemistry. What are the consequences of a molecule being three-dimensional? What are the consequences of how it is arranged three-dimensionally? So to start, I would like to look at something in art, Rodin's sculpture, The Cathedral. And what I'd like you to do is take a minute and try to make this structure with your two hands. It doesn't quite work, does it? Why not? Well, that's a right hand, that's a right hand. It's two right hands, and you have a right hand and a left hand. And stereochemistry is related to this. Many molecules, many biologically relevant molecules, have a property called chirality, which comes directly from the Greek word for handed or handedness. And so there are many molecules in organic chemistry that we say are chiral, that they are handed. Well, what does it mean to be handed? Have you ever thought about that? You know, okay, I have a right hand and I have a left hand, and they're the same but different. They're mirror images of one another. But, you know, if I had a right hand and another right hand, that would be very different. You know, I would do things differently than the way I am right now with a right hand and a left hand. We've talked a lot in our units on NMR about symmetry. And so for the rest of this lecture, I'm essentially going to be talking about asymmetry. So something is chiral, whether it be a molecule or non-molecule, if it has a non-superimposable mirror image. So, you know, again, the easiest example to see, I think, is right in front of you. It's your hands. Your hands are chiral. Or more, your right hand is chiral, for example. Your right hand is chiral because it has a mirror image, your left hand, but they are non-superimposable. I can't, like I said, put my left hand where my right hand is. I can't put my right hand where my left hand is without making a change in how the hands are arranged three-dimensionally. When a molecule has a non-superimposable mirror image, there are some things about these pairs of chiral molecules, these pairs of enantiomers, I'll define that in a minute, that are the same, and some that are different. Just like there are some things about your hand, there are many things about your hands that are the same, but there are some that are different. So let me start by drawing the amino acid alanine. Many of you have probably heard of alanine. You know, it's found in proteins. It's a very common amino acid. So here's alanine. Alanine is an example of a chiral molecule. Alanine has a non-superimposable mirror image. Why is that? Well, alanine contains something called a chirality center. Chirality center is an atom, usually a carbon. If it's a carbon, we can call it a chiral carbon that has 4 unique groups attached. So this carbon is attached to a carboxylic acid, it's attached to a primary amine, it's attached to a hydrogen, and it's attached to a methyl group. So 4 unique groups. Why is it? What is special about this? So what's the hybridization of this carbon? Well, it's sp3 hybridized. Therefore, it must be tetrahedral. So There is something then that I haven't shown when with this chiral molecule, and that is its three-dimensional structure. If this is a tetrahedron, then okay, I can have two bonds in the plane of, in this case, in the plane of the screen, but then these two bonds are not in the plane of the screen. So I'm going to erase them, and what I'm going to show is one of these groups is for the natural version of alanine, the hydrogen is as drawn coming out of the screen at you. And so I represent that by drawing something called a wedge. So it's just like a bond, but it's shaped like a triangle, and I shade it in like so. And what this says is, okay, here's the carbon, the H is coming out of the screen at you. And what that means then is this methyl group must be going behind the screen. So going behind me or you. Well, no, not behind. So the methyl group is going behind the screen, and we represent that with something we call a dash or a hash. Same sort of thing. We start and make a series of lines like this. So this represents a bond. You can see it's also kind of triangular shaped. And this says, okay, this methyl group is behind the plane of the screen, behind these bonds right here. So if I use a model to represent this, I get something like this. So you can see, here's the plane, here's the carboxylic acid, here's the amine, here's the central carbon. And you can see the hydrogen is coming out in front, and so that's represented by the wedge. The methyl group, you can see it, it's on the molecule, but it's coming behind, and so that's represented by the dash. And so, again, the chirality center is this carbon atom that has four things bonded to it. All right, so we have a fancy chemistry word when we want to describe a pair of molecules that are mirror images of one another, and that is enantiomers. The physical example of this, again, would be the hands. My hands are enantiomers of one another. They are non-superimposable mirror images. But my hands aren't molecules, my hands are a collection of molecules. For drawing molecular enantiomers, well, there are a couple different ways of doing it. Let's draw a mirror plane. And so that's my plane there. That green is the plane. And so for the enantiomer, let's see, I'll draw the enantiomer in red. Essentially, we just draw the mirror image. So rather than putting the carboxylic acid on the left, or on the right, I'm going to put it on the left. So there is the enantiomer of alanine. So here's the original alanine. H coming out at you, methyl group coming behind me. And if I do this like I have it on the screen, here is the mirror image of the alanine. So you can see now the amine group on this one, it's on my right. On this one, it's on my left. If I try to flip these molecules around so that they become superimposable, so that the amine and the carboxylic acid are on the same side, well, now look, what was a wedge, what was coming out at you, the hydrogen is now behind the plane, and the methyl group is in front. So the other way of drawing this is to draw the stuff in the plane of the board is the same, but then switch what's the dash and what's the wedge. So here I have hydrogen as the wedge and methyl as the dash, so I'm going to switch them. I'll put methyl as the wedge and hydrogen as the dash. So these two molecules are also mirror images of one another. If you build models, you'll be able to twist and flip it around and figure out that the two things that I've drawn using the red pen here are in fact the same molecule. They're just different orientations of that molecule. So finally, what we can say, we've talked a lot so far about isomers. Isomers are pairs of structures with the same molecular formula. And as it turns out, there's more than just the isomers that we've talked about, which are called constitutional isomers. So for example, there's a molecule called beta-alanine, which is a constitutional isomer with natural alanine. So there's alanine, and here's beta-alanine. And beta-alanine, it's the same molecular formula, same number of carbons, hydrogens, oxygens, and nitrogens, but it's arranged, in this case, in a linear form rather than in this branched form. So those two are constitutional isomers. If they do have the same connectivity, if they're superimposable, then they're one and the same. If you go back through the video and say build a model of the two alanines that I drew in red, you'll figure out that if you flip them around, move them around, you can see that they are in fact the same structure. If they're not superimposable, then they are stereoisomers, and that's what we've been talking about today. So things that have the same connectivity but are not superimposable. If they are mirror images, then they are enantiomers. There is also a type of relationship that I have not talked about today that we will talk about in class coming up called diastereomers. So a physical example of a diastereomer, we've talked about, all right, your hands are enantiomers. Well, what if I could take my middle finger on my right hand and flip it around? So these fingers could bend forward, but my middle finger would bend in the other way. Well, now it's no longer a mirror image. It's the same connectivity. Middle finger is still in the middle. Same connectivity, but it's not a mirror image because even though these fingers would be the mirror images, the middle fingers would not. They would be the same. That is an example of a diastereomer. We'll talk about molecular examples of diastereomers in class coming up. So, see you soon.